Okay, everybody is very welcome to attend today's web seminar by Professor Xiao Wen from MIT. We'll talk about from topological order to origin of elementary particles from algebra to geometry. To you, Xiao.
Okay, thank you very much. Thank you for the invitation. And today I'm going to talk about a new kind of quantum material, which have a new kind of order called a topological order. And I will discuss how that may affect our worldview. And we know that our world is very rich and complex. We have a lot of material, have a lot of phase and phase transition and things like that. And but our understanding of this our world is actually goes through the cycle of discovery and unification, more discovery and more unification. In a sense, through experiments, we discover a lot of facts, and then after we get too much facts, too much knowledge, we want to understand those knowledge and try to unify them. And then after unification comes with a new theory, then we have more discovery and more unification. Okay. It's actually, each unification is like a revolution in physics. And each revolution really brought us into a new world. We view our world differently. And many fundamental concepts may be changed. And even the language may need to be changed. And so that means that we need to introduce new mathematics to describe the new world. So that's kind of a revolution in physics. So the first revolution we can say is a mechanical revolution. It unified the phenomena of falling apples and the planet motion on the sky. So falling object on Earth and the planet motion on the sky seems very different, but actually they are really the same kind of mechanical motion. At that time, our worldview is that all the matter are formed by particles, okay, and each particle satisfies Newton's equation, okay. Then from this, we understand, we feel that we understand everything via this particle point of view. And what is amazing is that at Newton's time, to write down his equation, he had to develop new mathematics, because the mathematics to write down this mechanical law is not developed at that time. So Newton and Leibniz have to develop the calculus in order to describe this, to formulate this theory, a new theory, the law of motion for the particles. Okay, the second revolution we can say is a electromagnetic revolution, which unify the phenomena of lights, electricity, the magnetism, and the lights. Okay, and however, here I want to say that there is another way to understand this electromagnetic revolution. That is to view this as a discovery of a new form matter, which I call wave-like matter. So this electromagnetic wave is a new kind of matter, not like a particle-like matter in a Newton theory. So we have really a new type of matter. So I try to view this is a very important aspect of this electromagnetic revolution. And this new form of matter, of course, satisfies a different equation motion, a different law. So that is the Maxwell equation. Then later we find that the Maxwell equation is closely related to the mathematical theory called a fiber bundle. So therefore, fiber bundle is the mathematical foundation for the Maxwell equation. So that is the second revolution. The third revolution, I call this a relativity revolution, where there's a space, time, and gravity are unified. And so we can view this relativity revolution as a discovery another wave-like matter. which is a gravitational wave, which corresponds to the deformation of a space itself. So in addition to the particle-like matter of Newton and the wave-like matter of Maxwell, then we have a second wave-like matter. It's a gravitational wave. And it satisfies a different wave equation. It's Einstein's equation. The new mathematics involved would be the Riemann geometry. Okay. And so actually this it takes about 100 years to confirm Einstein's prediction. So the gravitational wave is only discovered recently. So this fiber bundle picture of electromagnetic interaction, and also the tangent bundle picture of the of gravitational interaction. It's a very beautiful. The curved space and the curved fiber bundle are really related to the fundamental interactions, and so it's really a very beautiful mass, and kind of physicists really like them really a lot, and so this kind of form a geometrical view of our world. So basically, all our interactions are some kind of geometry, some curvature, and so this kind of geometrical view of world kind of dominated physics. So this manifold fiber bundle became very important topic in physics. People use that to formulate a quantum field theory. So this is kind of basically mainstream of physics, geometrical view. But somehow this geometric view is challenged by the fourth revolution I mentioned. It's called a quantum revolution. So in this quantum revolution, this particle-like matter and wave-like matter are unified. So all these phenomena for hydrogen spectrum, interference, blackbody radiation is a microscopic phenomena from the microscopic world. Is unified, and so the main thing really the unification of a particle-like matter and wave-like matter. So basically, the matter is neither particle nor wave, or maybe the both particle and wave. So it's kind of very strange things in quantum physics. It's very hard to accept. So the new mathematics is totally different. It's a linear algebra and a tensor product in the linear algebra. So this is a mathematical language for quantum physics. Really sign that we start to deviate from the calculus world. It's a geometric view, basically kind of similar to the calculus. It's coming from the calculus. And here now, the quantum mechanics seems to present some algebraic point of view. So it's a linear algebra and those kind of algebraic kind of mathematics are involved. So the essence of quantum theory is really that the very notion of existence is changed. For example, let's using a spin as an example. The spin up is existence. We call this a qubit zero. You can say that. And the spin down is also existence. We can say that's this qubit one. Okay. But the quantum theory tells us if a spin up is the existence, spin down is the existence, and some kind of addition or composition of the two must also be an existence. They also exist. So actually, this spin up plus spin down correspond to spin in a horizontal direction, say in the x direction. And the spin up minus spin down is like spin in a minus x direction. So those are, this kind of superposition also exists. So that's kind of called the superposition principle. So under superposition principle, we can understand why the particle and the wave are kind of a similar thing. Because the particle have this location, like a location x1, x2, that's a particle location. And we can have a superposition of those existence. It's like a particle, this x1 is the existence, x2 is also existence, and some kind of superposition of x1, x2, x3 are also existence. And this superposition coefficient, this kind of linear algebra, this coefficient, expansion coefficient, it's like a wave. Yeah. So in this sense, the position is like a particle, but this expansion coefficient like a wave. And they're actually all describing some kind of existence, the particle or wave existence. So that's really a particle wave duality. And so this is really very striking. And so quantum theory is pretty hard to understand because the very notion for existence is so much modified. And actually, this superposition principle have another consequence. Basically, this consequence tells us this is already unification between matter and information. At the beginning, it sounds very strange. Usually we say the information is carried by matter. So information is some attribute of some matter. Like spin up, electron is a matter. Spin up electron is information. Spin down electron is another information. So it's a kind of attribute information. But however, in the quantum theory, it tells us that the frequency and energy are related. And we know that the frequency actually is a property of information. We don't care what changes. Any change is a frequency. So frequency represents change, but anything changes is a frequency. But the quantum theory tells us whenever you have a frequency, you times h bar, this is Planck constant, you get energy. So frequency and energy are almost the same thing. It's kind of like the temperature and energy is the same thing. Because at the beginning, we say temperature and energy are very different concepts. Now we know that the temperature and energy is the same thing. They are related by the Boltzmann constant. The Boltzmann constant is like a conversion factor between temperature and energy. I also can compare to this pound and kilogram is the same thing. They both different unit of a same concept. So in some sense, the frequency and energy is a quantity to describe the same thing with different unit. And the Planck constant is like a conversion factor of this between these different units. And also, according to relativity, energy and mass are related. And both energy and mass are property of matter. So therefore, property of matter and the property of information are directly related. So this gives us really a very strong hint that the information and the matter may be the same thing. So that is so that's kind of message from quantum mechanics. And here I try to push this point of view to the extreme and really just accept that matter and information is the same thing, And so we try to say that the matter arises from quantum information. But how can that happen? What I mean by that? Okay. So one point of view is following. We say that space is a qubits ocean. Quantum information is a qubits. Is a 0 and a 1 is a bit, and the quantum bits is a qubits. And we view the space as an ocean of qubits, as a collection of many, many qubits. So that is a quantum information. Collection of qubits is quantum information. And the space itself is formed by this quantum information. So in some sense here, I try to say that every qubits, the qubits represent existence. If there's no qubits, there's no existence. So there's nothing between two qubits. The qubit is all we have for the space. There's nothing between qubits. Okay, so that is a kind of a picture. We have many, many qubits. So each dot is qubits, and the black and white are two states of qubits. Okay. But once we have this qubits ocean, then we can understand how the elementary particle arises from quantum information. Because according to quantum mechanics, the particle is basically a wave. So origin of a particle corresponds to origin of a wave. And when you have a qubits ocean, these qubits may fluctuate. So 0 and 1 can change. And this fluctuation of qubits in the qubits ocean, it kind of gave rise to the wave. And that wave corresponds to our particles. Okay. And also those qubits are not independent. There's some entanglement between qubits, and that gives us a sense of space. So neighboring qubits are entangled. So this can define whether space is one-dimensional, two-dimensional, three-dimensional. So this kind of entanglement structure define the sense of a space. So that's kind of a idea. This deformation of entanglement gives rise to wave, and that is elementary particle. So that's kind of a basic idea. And actually, this idea is not that crazy. In the sense that when we view space as a collection of qubits, it actually corresponds to the space itself is a dynamical medium. It's not something empty state. The space is not a nothingness. The space is very dynamical. And this point of view have experimental confirmation, basically via this cosmic effect. When you play the two metal plates near each other, it modifies the quantum fluctuation of the space itself. And that led to the attractive interaction between two metallic plates. Okay. And this attraction has been measured. So we try to say that the Casimir effect is experimental evidence that the space itself is a dynamical media. And here we assume this dynamical media probably is this Cubist ocean. Okay. But do we really believe all the element particle and interaction, or they all come from the ocean of qubits? You know, this our world is very complex, and they are described by the so-called standard model. The standard model is very complex, actually. It have a lot of input, you know, and we call this input to the standard model because it's a wonder or mystery of our universe. Okay. The first input is that we have identical particles. Okay. So like when I have a hydrogen atom in the position X and another hydrogen atom in position Y, these two hydrogen atoms are totally identical. There's no way to distinguish them. Okay. However, if you only have identical particles, or in particular identical bosons, then it's a fit qubits picture very well, because we can view this 0 qubits as a background, this 1 qubits as a particle, this 1 qubit may move around. Okay, and so that's this particle move around, and certainly the 1 qubits at different place, they're really identical. There's no other attribute, you know, to distinguish them. So therefore, identical particle really is very compatible with this qubits ocean picture. Actually, it's a way almost suggests that we have a qubits ocean. And when we have this qubits ocean picture, it's very easy to understand identical particle. Otherwise, using the empty space picture, it's pretty hard to understand why all the particles are exactly identical. But however, we not only have identical particle, we also have this some particle like a photon correspond to wave that satisfy Maxwell equation. Okay, and we also have a waves or particle satisfy the Yang-Mills equation, a different differential equation, different wave equation. Okay, and even more strangely, there's a particle like an electron and quark. They have so-called Fermi statistics. Okay, so in Fermi statistics, this particle also described by waves, but it's kind of a very strange wave. We have to assume the amplitude of a wave is described by the anti-commuting field. It's really, really strange, you know. And those kind of Fermionic particles carry fractional angular momentum, like spin 1/2. It's also a very strange thing. And also we have right-hand fermion, left-hand fermion, and only left-hand fermion couple to the Yang-Mills waves, and the right-hand fermion do not couple to that. And we have Lorentz symmetry and the graviton, you know. So we have a lot of fundamental property which we don't know where they come from. So we accept those properties as a fundamental, and assume them, and using those to build a standard model. So that is our understanding at the moment as a standard model. But here we want to ask where those fundamental properties come from. We have to make 8 assumptions. That's too many. Can we make a fewer assumptions? Where do they come from? And here I want to answer. And so this question actually almost like ask, can geometry emerge from algebra? This kind of Maxwell equation, Yang-Mills equation, and the Einstein equation, they kind of equation for the geometry, for the manifold, for the fiber bundle. Okay, and so that they belong to geometry. But when you do the qubits, the qubits is algebra. There's something discrete, and the kind of collection of qubits, which algebra, discrete algebra, produce those continuum geometry and equation motion. And even this Fermi statistic on the computing field, can we really do that? So at the beginning, it looks like it's very difficult. It's almost impossible to do that because those properties are very fundamental to be explained by this very simple qubits. So that's the difficulty we are facing. Here I want to make a remark that this trying to have a elementary particle emerge from qubits motion have another point of view. We can ask, can we use quantum magnets, this quantum material we call quantum magnets, to simulate a standard model? Because this qubits ocean actually is quantum magnets. We can view each qubits as electron spin coming up and down. So that is a quantum magnets. And so therefore, when you have a quantum magnets, we actually have a qubits ocean. And then the question is that can we design some interaction between those qubits or between electron spin, such that at the low energy, this collective wave in this electron spin ocean satisfy Maxwell equation, for example. And we can also view this qubits ocean as a boson gas, like the 0 qubits like a site with no boson, and 1 qubits as a site with occupied by 1 boson. So this so we can also view this as a lattice boson gas. So we have similar question. In the lattice boson gas can be produced in the cold atom system. In the cold atom system, we can have this lattice boson gas. Then we can also ask similar question. Can we use the lattice boson gas to simulate a standard model, to produce a standard model, like produce a wave that satisfies Maxwell equation and things like that? So that is the question. So therefore, using qubits ocean to produce a standard model is also kind of condensed matter problem. Can we use some condensed matter material to simulate a standard model, to simulate our vacuum, our space? So that's became this kind of question. So let's give it a try to see what we can get. Let's using this boson gas language to describe a qubits ocean. So we have a boson gas. Okay, those are particles. This black dots particle, and the white background is like a qubit 0. This black one is a qubit 1. Okay, and then what is the wave in the qubits ocean? In this kind of qubits ocean, these boson gas are described by the quantum states, some kind of quantum states, which I will describe in a moment in more detail. And they are kind of a superposition of all position of particles. So one of the quantum states, or the so-called many-body state, is a superposition of all these all the particles. Okay. And then that's Guan states. Now what is the collective excitation? The collective excitation are just a density wave. So somewhere we have a more particle, otherwhere we have less particles. And this density wave is kind of a wave in this kind of a particular qubits ocean. And this wave satisfies the equation. It's a standard wave equation. And but unfortunately, this wave equation is not a Maxwell equation. It has a wave, it's a something, but it's not a Maxwell equation. And actually, this kind of wave equation describes so-called massless spin zero boson. But a light or photon is a massless spin one boson with a helicity plus or minus one. It has only two components. So the light wave have only two polarization. Okay. So this is a wave and wave equation, but the wrong equation. So this kind of wave is a something, but not light wave, not Maxwell wave. Okay. So then we try another thing. Let's try crystal. So if a liquid do not work, let's try crystal. And in the crystal, we also have a wave. We also have density waves. In the crystal, there's a particle arranged in a very regular array like this. Okay, that's a crystal. And again, we have a density wave. There's somewhere we have more particle, otherwhere have less particle. That's density wave. But in the crystal, we also have a shear deformation. And this shear deformation do not change the particle density, but change their configuration. And so therefore the wave in the crystal are described by a different wave equation. We call that elasticity equation. And this equation have this wave in the crystal have a one longitudinal mode, but a two shear mode, two transverse mode. Because in 3 dimensions we can shear even up or down or left or right. They have two directions to shear. So it's kind of like a spin one boson, but it's too much. This sound wave in the crystal, this is called a sound wave, have a helicity. It's a spin one boson, but have a helicity 0 and plus minus 1. We have this one actual helicity. But the Maxwell equation have only two transverse mode. The sound wave have two transverse mode, but also have additional longitudinal mode. That's a compression mode. So again, it's kind of close, but not quite there. So we don't know how to get Maxwell equation. We get the sound wave, but not Maxwell equation. So this really reflects our frustration. In the condensed matter system, we study all kind of many-body Guan States, and they have all kind of wave, all kind of wave equation. But for the long time, we consider all kind of order, all kind of wave, and but we never find a particular material, a particular order, which gave rise to the Maxwell equation. At the beginning, after Maxwell proposed his equation, he actually draw this kind of wheel model, a gear model. They try to say that maybe this mechanical motion of all kind of gear or rotors can simulate the wave which satisfies Maxwell equation. Yeah, but this gear model don't quite work, and but even after quantum mechanics, we consider all kind of quantum material. We still have difficulties to find Maxwell, to find a media which give rise to wave that satisfy Maxwell equation. Okay, so it's kind of a failure. Yes. Go ahead.
My question goes to not the last slide, but the previous one, so-called what you call the liquid. Not this one, the previous one.
Yes.
Well, we all know that Madelung in the 20s proposed the transformation to picture in hydrodynamic terms an equation, a mean field equation that we now call it Gross-Pitayevsky. Would you regard this as a failure to capture features that you're looking for?
Actually, I'm not familiar with what you mentioned. But the question is whether that wave equation is a Maxwell equation or not. You say that's a Maxwell equation? So here I'm really describing so-called superfluid. We have many particles. You have a particular ground state. That is superposition of all particle configuration. That's a superfluid ground state.
Sure.
And then what is the wave in this superfluid? We find it have a wave, it have a wave equation. It's just the form of a wave equation is not what we want. It's not a Maxwell equation. It's something else. Maybe this called, I don't know what they call it, Euler equation. Whether this equation have a name, I don't know. And also for the solid, there's a crystal. We have this elasticity equation. It's also a very nice wave equation, but just not the Maxwell equation, And so we are looking for a media which produce a Maxwell equation. That's an ether, After Maxwell write down his equation, people believe deformation of a certain thing gave rise to Maxwell equation, or even call that ether. But for 150 years, we're looking for ether, but we couldn't find it. We found a lot of things, but none of them gave rise to Maxwell equation. Just gave rise to some other wave equation. So that is the frustration I'm talking about.
Thanks.
Okay. And then in 80s, actually, people study this semiconductor discover so-called quantum Hall effect. That is electron gas on the surface semiconductor and a strong magnetic field can form something some kind of strange quantum matter. And also in some kind of triangular lattice, some material with a triangular lattice, the electron spin may form a spin liquid. Okay. And the quantum Hall state and this spin liquid really contain a new kind of order, before when we discuss let me see. Yeah, maybe it's when we discuss the Guan States, we say the Guan state, the electron spin forms some pattern, maybe either all point up or all pointing down. There's some pattern, some orientation pattern. And this pattern kind of like the break symmetry, and there's a Landau symmetry breaking theory to describe all kinds of matters. But this kind of symmetry breaking theory seems fail to give us this Maxwell equation. But then in 1980s, we find a new kind of quantum material which go beyond the symmetry breaking theory. And we call this new kind of order a topological order, So that represents something, new kind of order, new kind of material. And, we studied all kind of old material. We couldn't find the Maxwell equation. But maybe this new material, new order, maybe give us some new hope. Maybe you can find the Maxwell equation in this new kind of order. Okay. So here, let me just slow down a little bit. And so what is this topological order? What is this new material? Actually, this topological order, new material are really a property of so-called quantum system, or quantum many-body system. So what is a quantum system? What is quantum states? So here I will give a little bit more mathematical definition. A quantum states actually correspond to the following. It have a Hilbert space, but this Hilbert space have a tensor product decomposition. So the big Hilbert space is a tensor product of many little Hilbert space. And each little Hilbert space is denoted by a vertex here in this graph. So each point is a little Hilbert space. And the collection of all those points are big Hilbert space. So this actually is a mathematical definition of a Cubist ocean. It's this kind of a collection for a little Hilbert space. Okay. And certain on each little Hilbert space is finite dimensional. For qubits, it's a two-dimensional vector space. Qubits only have two states, up and down. So that's two-dimensional vector space for qubits. Okay. And then we also have a Hamiltonian to define the dynamics of the quantum system. And the Hamiltonian basically is a Hermitian operator acting on this big Hilbert space. But the Hamiltonian have locality. That is it's a sum of operator which act on the individual little Hilbert space, or some kind of neighboring tensor product of a neighboring Hilbert space. Okay. So the Hamiltonian have this local structure. So basically, this kind of structure defines the quantum system. So the quantum system is this a collection of little Hilbert space and this local operator whose sum give us so-called Hamiltonian. And then, if you diagonalize this Hamiltonian in this big Hilbert space, we get eigenvalues. This Hamiltonian is a Hermitian operator, so we have real eigenvalues. And so this graph just describes these real eigenvalues. And in a particular state we call the gapped state, gapped quantum state, is that this spectrum of a Hamiltonian have a gap at a low energy. So this below the gap we call the ground state subspace. We call the ground state. And above the gap, that's the excited state. And there's a gap. And this gap is approached to some finite value when the system size is getting bigger and bigger. So the number of qubits n go to infinity, and this energy gap remains finite. And but below this energy gap, we have a nearly degenerate. These two energy level their energy gap go to 0. So we have nearly degenerate states. So this is a particular quantum system we call the gapped quantum system. Okay, so this is kind of like a mathematical definition of a quantum system and quantum states, or maybe they can say that the qubits ocean is something like that. And the dynamics of qubits ocean are described by this Hamiltonian. So we have this spectrum. Okay. So therefore, in condensed matter physics, we are interested in this so-called Guan states. So the Guan state basically is the state with the lowest energy, or maybe there's a few states with the lowest energy. So that's we call the Guan states. And we try to say that what kind of how to characterize these Guan states. You know, this Guan state is just a vector in this very big Hilbert space. You know, n is very big. N is like a 10 to the 23. And this dimension of this vector space is a 2 to the n times 23. So it's a very, very big, huge dimension vector space. So therefore, to describe this vector, we have so-called wave function. That is a expansion coefficient of a vector on the qubit basis. You have this kind of wave function, which contain like a 10 to the 20 variables. So it's very hard to visualize such a wave function. It's very hard to understand the structure inside this wave function. You know, how do we see this different wave function? And so usually people study the symmetry of this wave function, whether this wave function invariant under certain symmetry transformation. And that led to Landau's symmetry breaking theory, using symmetry breaking and symmetry property to characterize different Guan states. Just to study whether this wave function is invariant under certain symmetry transformation or not, using that to understand this Guan state. But however, to have a topological order, we need something beyond the symmetry, not symmetry. So here's the idea that we put this wave function on the space with different topology. So like in two-dimensional space, we may have a sphere, we may have a torus or genus Riemann 2 surface. Then we put this the quantum gas, the wave function of a quantum gas in 2 dimensions on this different global topological the space with different topological properties. And then we find that this wave function may have a different degeneracy. This Guan state degeneracy below the energy gap may be different. Like on a sphere, the degeneracy is 1. On the torus, it's D1. On the genus 2 Riemann surface, D2. So we can use this degeneracy to describe the different wave function. Okay. And that's actually led to this topological order. You know, this many-body wave function characterized by this Guan state degeneracy is a topological order. But then you may see the following. You know, why we have a degeneracy? Actually, before this, people think if you Hamiltonian have no symmetry, we have a generic Hamiltonian, the Guan states are unique. There's no degeneracy. Why we have degeneracy? The degeneracy should only be accidental. We should not have degeneracy. But actually, we have this topological order really coming from this some kind of protective Guan state degeneracy. This degeneracy is not accidental. It's always there. Actually, degeneracy became better and better when the system size go to infinity. So this kind of thermodynamic emergent property of degeneracy, and that is really the heart of a topology order. So to understand this degeneracy, it's really coming from the quantum information. That in the quantum information, we have many qubits, we have entanglement. But when there is entanglement, we have very interesting phenomena. That is, if you know every part, we still do not know the whole. So let me give an example of this quantum entanglement. Why knowing every part still do not allow us to know the whole thing. For example, let's consider two spin states, and they are entangled. One entangled state is up plus down. You know, the two spin up plus two spin down. This is also existence. Another wave function is a two spin up minus two spin down. That's another wave function, or another vector in the vector space. You can say that. And what is the parts? The parts is that, and let's only look at the first spin, and we do not look at the second spin. When you look at the first spin, we say the first spin can be up or can be down. There's a 50% chance for the first spin to be up and 50% chance to be down for the first state. But if you look at the second state, we also see the 50% up, 50% down for the first spin. We don't see this minus sign, actually. So therefore, if you only look at the first spin, then our second spin individually, we just see the first spin either up or down, and the second spin either up or down. And for the minus state, the same thing, either first spin is either up or down, the second spin is either up or down. So therefore, we know every spin individually, but we still do not know the whole. We do not know the whole wave function. So this is really some kind of a characteristic property of entanglement. The entangled many-body state have this property that knowing every part still do not specify the whole. And so actually this explains the degeneracy, because remember that the Hamiltonian are local interactions. They only correspond to interaction between qubits, nearby qubits. So that's local. So Hamiltonian only see the parts. So when you have entangled states, every part looks similar. So to the Hamiltonian, they look similar. But the whole wave function can be different. So therefore, that's why you can have two different wave functions with the same energy, because every part looks the same, so it has the same energy. But they are still different wave function. So that's why you have degeneracy. So therefore, this degeneracy from topology order are really coming from this entanglement. Okay. So now let's try to understand what is entanglement from this some example. Let's again consider two spin. We have two spin 1 and spin 2. And if the spin 1 is up, spin down is down. So this we call the product states. And this kind of corresponds to this tensor decomposition is a product states. And entangled states really like we have like up and down plus down up. So these are entangled states. Okay. Then we have more entangled states like up plus down plus down up plus up down. You know, it's just all the possible sum of a spin configuration. That seems more entangled. But actually, it's more entangled. It's actually not more entangled. Actually, it's unentangled. Because this kind of superposition can be written as an up plus down tensor product with up plus down. We know up plus down corresponds to the spin in the horizontal direction, say in x direction. So it's a product state of x state for the first spin and x state for the second spin. So it's unentangled. So the entanglement is a little bit tricky. It's not just a superposition means entanglement. It's some kind of superposition which cannot be written as a tensor product form. That represents entanglement. In condensed matter physics, we study a lot of many-body states, but mostly they correspond to unentangled state, like this antiferromagnets. We have spin up, spin down, spin up, spin down, this kind of spin pattern for the electron, we call this antiferromagnets. And that's correspond to unentangled states. And we may have a short-range entangled states, which is in this pair of electron, we have up and down plus down up. We call it dimer. Those are entangled. And so there's in general, we have the entangled states. But however, if you group these first two vertex as one side, and the second two vertex as another side, then they became unentangled. So then in this kind of structure, we call they are short-range entangled. And maybe let's say the superfluid order. The superfluid order is a superposition of all the particle positions. That looks like entangled, but actually it's not. It can be viewed as a superposition. It's a tensor product of a state which on each space point we have no particle superposition with one particle, superposition with two particle. So on every space point we have this kind of superposition state, and their tensor product after expansion give us the superposition of all particle configuration, and that is a superfluid state. But the superfluid state is actually unentangled states. Okay, so in some sense, I would say that when we try to using the when looking for the Maxwell equation from all kind of quantum materials, and we're actually looking for also those unentangled quantum materials, and those unentangled or short-range entangled quantum material do not give rise to the Maxwell equation. So therefore, we should looking for the long-range entangled quantum material. Actually, topology order is really means the material have a long-range entanglement. That's give rise to topological order. So how to get this long-range entanglement? Well, we know that the superposition for all possible spin configuration is not entangled. It's not long-range entangled. It corresponds to the spin in the horizontal direction. Every spin in the horizontal direction is a product states. So one way to get the long-range entangled states is not to sum over all spin configuration, but to sum over a subset of spin configuration. Here, the subset is that we view the, say, up spin as a background. And the down spin, we assume down spin form a string. Okay, form a string. Then we only sum over all the string configuration of a down spin. The string from a loop, actually. So we only sum over a loop of a down spin configuration. And that is a partial sum. Because assuming the down spin from a loop and only sum over loops is a partial sum. It's not summing over all spin configuration. And then this is also called a quantum loop liquid. And this loop liquid have a long-range entanglement. And you can also have a different loop liquid. For example, you can have a loop liquid of a summation for all loop with a plus sign in front of all the superposition. Or we can have also plus or minus sign in front of superposition, like a different superposition. And this sign depends on number of loop, whether even number of loop or odd number of loops. Okay. So those are two different quantum wave function, and we think they have a different long-range entanglement, or they have long-range entanglement. Okay. So okay, maybe let me skip this part, and yeah. So actually, this kind of loop liquid have a topology order, and so why? Because of following. You know, let's consider space is a torus. So this square represents space, two-dimensional space, which is torus. And we have a lot of loop in the torus. But however, we notice that if the number of loops going around the torus can be even or odd. So actually, we have 4 different configurations. Like the number of loops go around the torus is even in x direction, odd in x direction, or even in x direction, odd even in y direction, or even in y direction, odd in x direction. So we have 4 sectors. And these 4 sectors, they all look similar locally. If you only look locally, this wave function seems for all these sectors are different, are all the same. But globally, these different winding number are different. So that's give rise to 4 degenerate Guan states. And this, I want to say that this loop liquid can fluctuate. The fluctuation of loop liquid involving, just a moment, involving this kind of move. For example, the string can change its shape. Okay. They can also reconnect. They can reconnect in this way. They can so this kind of configuration can change into this kind of configuration with a minus sign or without minus sign. So if without minus sign, the wave function is a superposition of all different loops. But if I put a minus sign, this is superposition of a plus with a superposition of loops with a plus minus sign. Okay. So, but however, this kind of reconnection of a loop, if you look at this picture, do not change this evenness or oddness. So this even odd are invariants of a loop reconnection. So that's why we have a 4 sector, all different loop in each sector can change into each other, but the different sector do not change to each other. And so that's, and also those different sector, they locally look the same. So that's why you have a degenerate Guan states. So this is the reason why this loop liquid gave us a long-range entanglement, gave rise to topology order. That's kind of new kind of matter really coming from this kind of a long-range entanglement. But amazingly, this long-range entanglement can give rise to Fermi statistics. Remember, the Fermi statistics is something, and also spin 1/2 is something very fundamental as an input of standard model. And here we have a loop liquid coming from this Cubist model. Then in the following, I will explain this is spin 1/2, this fractional angular momentum, and also this Fermi statistics can come from this Cubist ocean coming from this loop liquid. So once you have a long-range entanglement, those spin 1/2 and the Fermi statistics will emerge. And so first we have to say that the loop liquid is a Guan state. The excitation in this loop liquid corresponds to end of string. You know, if a string have an end, then this end point is the excitation. One may say that the string is an extended object, not just 2 points. Why you say this extended string is a point-like excitation? Well, the reason is following. We remember in the background we have a lot of loops fluctuating. When you're putting this open string in this background, locally away from end point, it just looks like an ordinary original background. So we don't see this string is a part of open string or part of closed string. So we don't see this string. Then we only see the end string. So so open string in the background of closed string, only the end is observable. So like something different. So therefore end string is the excitation. And those excitations are called topological because we cannot create a single end by itself. We have to create a pair together. So this kind of a topological excitation. Okay. So it is this topological excitation when you view this end string as a single particle, as a single point, they may carry fractional angular momentum and they may carry fractional spin. Okay. So how do you argue this end of string may carry fractional angular momentum? First, let's try to understand fractional angular momentum. You know, fractional angular momentum in physics is representation of rotation group. It's O3 rotation group. And here we do 2 dimensions, so let's consider a 2-dimensional rotation group. It's O2 rotation group. And so usually we think when you do the 360-degree rotation, the state coming back to self. Okay. But however, when you consider one end of string, when you do the 360 rotation for one end of string, we change this straight end to this hooked end. And but this hooked end string can fluctuate. So this hooked end this right hook After this string reconnection on this neck, it can go into the left hook. So this right hook and left hook can flash into each other, so it can be regarded as same. And but however, no matter what kind of string flexion you include, this hooked end can never turn into the straight end. So therefore, this string end have two sectors. When we do this 360 rotation, you go from straight to hooked. And hooked can never go back to straight by string fluctuation. We have to do 720-degree rotation to change the double hooked can go back to straight. Okay. So this really try to say that the string end have two sectors. The 360-degree rotation is given by this 2x2 matrix. This straight going to hooked, hooked go back to straight. It's this one. So therefore, we have very kind of strange representation of a O2 rotation group. So we have this kind of representation. And this representation, the eigenvalue have a plus or minus sign. So this straight plus hook have eigenvalue 1. So under 360 rotation, they don't change sign. But the straight minus hooked under 360-degree rotation, this state changing sign. So then that's a spin 1/2. That's what we call this kind of changing sign under 360 is called a spin 1/2. So like a spinor representation of O2. Okay. And this is really the origin for fractional angular momentum. So you can see that this long-range entanglement can provide the fractional angular momentum, can give us a projective representation of O2 group. Actually, fractional angular momentum is related to the projective representation. And with this understanding, we also understand this Fermi statistics. So what is the Fermi statistics? The Fermi statistics actually is an exchange. We have a two particle, like a two end of string, two particle. We exchange two particle. Okay, so from A to B, we can exchange two particle. And then we consider fluctuations. Okay, then we can have a string reconnection fluctuation, then changing reconnect string this way, and we obtain this configuration. Then we can have another string reconnection fluctuation and go to this configuration. Then we find something quite interesting. That is exchanging two particles. It's like rotating one particle by 360 degree. You know, this became hooked. So it's like changing one straight string to hooked string. Okay. So therefore, the exchanging two end of string correspond to rotation of one end of string. Okay. Then we say that, then from here we immediately conclude that we have a spin statistical theorem. If a spin is 1/2, exchanging the two will get a fermion. If a spin is an integer, exchanging the two will give us a boson. So this is indeed what we discovered in particle physics. You know, all the fermions have a half integer spin. It's a projective representation of a rotation group. But all the bosons are a faithful representation of a rotation group. And here, using entanglement, using the end of string, we have an interpretation of that. So why we have such a relation. So from here we can see some kind of magic. That is, once we have a long-range entanglement, from a Cubist ocean, we can have something like a fractional angular momentum or projective representation of a rotation group, and a Fermi statistics, or some kind of representation of a braid group, non-trivial representation of a braid group, would appear from this long-range entanglement in the Cubist ocean. Actually, we can get even more. So let me skip it. We can get the Maxwell equation also, because once we have a string liquid, then we can ask what is the collective mode, what is the wave in the string liquid. Then naturally, you have a density wave of string. You know, somewhere have a more string, otherwhere have less string. So you have density wave of string. That is a wave in the string liquid. But however, the string density wave are described by a vector, not by a scalar. The density is described by a vector because a string have orientation. When you say more string, you have to say more string in which direction. So string have orientations. Okay. But also this because string form loops, then along the direction of string, the density cannot change. In order for string to change, density to change, the string have to have end. If string have no end, the density cannot change along the direction of string. It can only change perpendicular in the particular direction of string. So therefore, this vector field have a divergenceless, have a no divergence. Then now you can imagine we have a density wave of a vector field with no divergence. The wave equation will be naturally Maxwell equation. Because the Maxwell equation is the simplest equation which preserves this divergenceless property of a vector field. So actually, using more careful calculation, indeed we find this result. That is a wave in a string liquid gave rise to Maxwell equation. You can see this long-range entanglement of string liquid would give rise to Maxwell equation. Yeah, actually I will finish soon. And we can even get the Yang-Mills equation. Because we can consider we have many type of strings. String have a blue type, a green type, and the type may branch, may join together in certain way. Okay. Then we can have some kind of string net liquid. Rather than string liquid, we have a string net liquid. It turns out that using string net, the wave in the string net liquid gave rise to the Yang-Mills equation, which describes this electromagnetic weak interaction. Okay, strong interaction, and also weak interaction from the Yang-Mills equation. Okay. And also, this end string behave like a gauge charge, which coupled to the electromagnetic field, a string density wave, and the Yang-Mills equation, just like a charge, like a gauge charge. So this end string just like a gauge charge. So therefore, this string liquid, or more precisely, this string net liquid, it kind of simulates a standard model. So that's based on the main message. That if you start with Cubist ocean, we design the Hamiltonian such that the qubits form a string net liquid, some kind of string net liquid. Then from string net liquid, we can have a Yang-Mills equation and the Maxwell equation, and also a Fermi statistic, and etc. All these properties. And we know that the Yang-Mills equation, the Maxwell equation, coming from the Fermi bundle. Actually, Yang-Mills equation coming from this principal bundle of some continuous group, and the Maxwell equation coming from the principal bundle of U1 group. Okay, and so therefore this string net liquid can have the emergence of this vector bundle and provide the Maxwell equation and the Yang-Mills equation, and even the Fermi statistics. Okay. So this is really design. So in condensed matter right now, we are trying to looking for some material which can realize this string liquid or string net liquid. And then in the string liquid and string net liquid, we may have a emergence of a standard model, kind of like our universe. So that's a way. So it's possible to using Cubist motion, a Cubist ocean of quantum material to simulate a standard model. And so this topological order long-range entanglement allow us to do that. Okay. However, at the moment, we get everything except the last one. We still don't know how to simulate the Einstein equation. We consider all kind of string liquid, but those string liquid do not give us Einstein equation at the moment. So maybe something other things, maybe some membrane liquid or membrane net or something. But at the moment we don't know. Yeah. So it's not totally finished yet. Yeah. So at the moment, theoretically, we really try to find some material of entanglement where the Einstein equation can be emergent or not. Okay. So to summarize, it's really that the matter and the space probably can be viewed as a Cubist ocean or maybe quantum information, and the gauge interaction, Fermi statistics, and the space, and they maybe all come from this long-range entanglement. Yeah. Thank you very much. Yeah.
Thank you very much, Xiao Yang. To break the ice, I'd like to ask one question straight away, if I may.
Yeah.
Can you go back to a slide, I don't know, 24, something like that?
Yeah.
You
Okay,
showed
okay.
something that was quite intriguing, and yeah, previous ones, please.
Okay, yeah.
Okay, once more. Go back.
Which way? This 23?
Maybe back. Oh, okay, this one.
You mean this
So,
one?
yes,
Yeah.
this one. So, well, the third equality under the item sum over subset is,
Yeah.
I like it very much because it reminds me some work that I've done with Xin Liu in
Yeah.
BJUT.
Okay.
And so I interpret, let me see if we have similar or some analogous interpretation of this. I see the theta there.
Yes.
As can I interpret the theta if I were to interpreting the theta as ADA, the potential contribution in Chern-Simons action. We proved that, and then of course considering the number of loops, we proved that E2, let's say ADA integrated, satisfies the skein relation of Jones or Humphrey PT polynomial.
I see, yeah.
So I could see a bridge. I could see a bridge between what you mentioned and our work. And my question would be, in my naive interpretation of entanglement, then, according to what I just said, it would be related to global topological properties of loops. What do you think about that?
Yeah, they are very related, and but what I described here is a little bit different. This phase only depends on number of loops, and the Chern-Simons theory you describe is some kind of linking number.
Right.
And here we don't think of linking yet. We just think of this just a number of loops, even number of loops or odd number of loops. Okay, but however, the Chern-Simons theory described is really there. It's a falling, and so just a moment. So actually, the Chern-Simons theory described is really yeah, it's here, and so remember we have two loop liquid. Okay, one loop liquid is that this reconnection is a plus sign. That's equal with the superposition of all the loops. But however, if this reconnection gave you a minus sign, you have a minus sign here, then the loop liquid became this plus minus superposition of the loops, depending on even number of loops or odd number of loops. But actually, when you have this minus sign, then we find that here I skipped the under string have this spin a quarter, not 1/2 a quarter, because a 3/6 rotation would have this minus sign here. And this minus sign have this eigenvalue is I and minus I, so spin quarter. And the spin quarter, that means this became this anion, this became anion. Yeah, this we call samyang. So understream became samyang. Okay. And so really this really say that these two topological orders are different. This plus sign and minus sign, they have give rise to different topological order. And this samyang actually are described by the Chern-Simons theory you described. That is when the samyang is a particle in space-time, the trajectory is a word line. Okay. And this kind of statistics, exchanging to samyang, give you the non-trivial statistics, are described by this the linking of word line. And this linking word line is related to Jones polynomial and all this knots theory. Yeah. So in that sense, it is a trajectory. This understream can move around in space. The trajectory of this particle is called word line, And the linking of waterline give you some phase factor, and this phase factor is this statistics. And that phase factor can be described by this transamination theory, just mentioned, ADA. So in a sense, I want to say that this kind of string liquid, this kind of string wave function with plus minus sign, they simulate a Chern-Simons gauge theory, ADA Chern-Simons gauge theory. I didn't write down here, but so in condensed matter physics, that we can have this material with this kind of string liquid, and this material at a low energy are described by quantum field theory. It is this quantum field theory is the ADA quantum field theory you just described. So the Chern-Simons quantum gauge theory can be simulated by quantum material. Yeah, that's you can say that way. Yeah.
And let me go back again to this naive viewpoint. Yeah. I say naive because I know alternative views of this. When you talk about entanglement in this string liquid context, you really refer also to, I mean, topological linking, or more abstractly to relation between qubits.
You know, at the moment we consider two dimension. So it's really this. It's really qubits. You know, and so the string liquid string is breakable. It's really the string is just formed by qubits. So they are discrete. And here when you consider string configuration, because let's assume they are two dimension. So there's no linking. So my mainly emphasize they form this kind of the string, but this loop can be big and small. The loop can be very big. They can wrap around the system several times. So when you have this kind of a large loop liquid, then that's when we say we have a long-range entanglement. So link at this place, linking is not very important, but to have a large loop liquid is important. That's when you have a long-range entanglement. However, the linking became important if you think about the trajectory of an end of string. The end of string is particle, their trajectory is a word line. Then the linking of word line is important because it can characterize the statistics of an end of a string. So there's a little bit of twist here.
I understand, very clear. Yeah. Thank you very much.
Yeah.
So please, questions.
So, hey, Xiao, great talk.
Yeah.
Thank you very much. So I have a question about this loop and the string, right? Talk about this. How do that change? Because how do they relate to entanglements? You entangle, and then furthermore, what were they related to different kinds of particles, such as fermions and bosons? Are they different in entanglements related to strings and loops?
Yeah, great question. So actually, this is superposition for big loops. It's a one way to construct entangled states. You know, so here just to give example. So these are entangled states, and these are also entangled states. And the different superposition coefficient give rise to different entanglement, different long-range entanglement. Okay, but that's just a Guan states. Okay, but once the Guan state have this long-range entanglement, then the excitation is like a defect. So the Guan state like a pattern. So this superposition is a pattern. The break of a pattern is like a defect. The defect like a particle. So in this loop liquid, the defect is end of string.
Right. Okay.
So this end of string can be viewed as a defect in the loop liquid.
Right. So I understand that. Yeah.
And then I try to argue in the next few slides. This defect in the long-range entanglement can have weird properties. It's really because it's something from energy point of view, it's point-like because the string attached have no energy. We don't see them. But from quantum interference, from entanglement point of view, the string attached have effect. It can modify their angular momentum, can modify their exchange statistics. So it is this. That's how the entanglement come into life. They don't affect energy, but affect some kind of interference. And the loop liquid is simplest entanglement. We can explain this by some cartoon. And there are also string-like liquid is more complicated. And even beyond string-like liquid, there's even other superposition, even more complicated. So then it's a full mathematics, the category theory may have to come into play to really understand all general structure. But here, the key point is that the under string is a defect carry energy. The string itself don't carry energy, but they carry some kind of modify some kind of entanglement, and but physically it corresponds to modify the statistics and the angular momentum of this point particle. I think that's the main thing how it works. Yeah.
They also change. How would they change topology?
What we try to say that when the rotation, so you can see this end of a particle and the string form a repetition rotation group, but it's a projective repetition. It's a very strange projective repetition. So in that sense, I say that's kind of like changing topology, but it's not really topology in the other sense. It's a topology in the algebraic sense. So from unitary repetition to project repetition. Okay. So there's something dramatic change. So actually in condensed matter, we call this kind of phenomenon topology. It's not usual topology like apple or donuts, it's not that kind of topology. It's really the complete change of repetition. The Cubist they form a representation of a rotation group. If you rotate whole thing, you just representation of a rotation group. But the single end of the string can give rise to projective representation. So that's already something quite funny. Yeah.
Very good. Thank you.
So we call this a change of topology. Yeah.
Thank you very much. And the different boson and fermion how would that cast differently?
What? Could you repeat?
The different particles, different spin, for example. Quarter spin, half spin, and one spin. How would they be different in your string, and they similar? Is what you were saying? Right?
Yeah. So the following. So let me go back. And so maybe let me go to there. You can see we have two different ground state wave functions. This is equal weight superposition and plus minus superposition. And this corresponds to different ground state entanglement, different long-range entanglement in the ground state. And the end of string in these two liquids are different. Here end of string are boson and fermions. Here end of string are fermion and anti-fermion. So you can see the different long-range entanglement gave rise to different pattern of statistics. And here only boson and fermion are allowed, but here only fermion are allowed, And then you can imagine different entanglement. If I have more general entanglement, will give you more general things.
Very good. Thank you very much. Wonderful. Wonderful.
Other questions, please. Any question? I have one more to ask. Is a very basic. When you mentioned the gap in one of your slides, I mean, physically, what would be the most important ingredient? Of course, is in terms of energy, I believe. But would you be able to say, to pin down some physical property that would define this gap between ground state, fundamental ground state, and whatever else?
This is called a gap system. So I did not emphasize a difference between gap and gapless, and which is actually pretty important. And in physically, the gap material is like an insulator, and the metal is gapless. Okay, that means if a quantum material have a gap, means it don't respond. If you if you knock it, it costs fine energy to do any change. So they don't change. And for the insulator, if you apply electric field, you don't generate the currents.
Sure,
but for the metal, if you put the electric field, the electron would rearrange because there's many low energy excitation will rearrange. And after rearrangement, the newly rearranged states carry currents. And so they respond. And so actually, in physics, we are more interested in the gapless states. And the gap-state insulator is trivial. But recently, we find that that even gap states have a non-trivial thing, like a topology order, anions, fractional statistics. So even that is a very non-trivial. And also, the gap state in condensed matter system corresponds to topological quantum field theory in mathematics.
Sure.
So actually, study of topological quantum field theory corresponds to study non-trivial gap states. Before we don't realize topological quantum field theory, we think the gap states are trivial, there's nothing there. But now you know that the topological quantum field theory is very rich. So actually, that means the gap material is also very rich. It's not that trivial. And so therefore, so you can see that the study of topological quantum field theory or entanglement theory in mathematics can be viewed as a study this gap the quantum material in physics. And actually, that's a wonderful thing we try to do. That's experiments. We want to find a material which realizes entanglement theory. Actually, we have that. The quantum Hall states actually is a material which realizes entanglement theory. But there's many other topological quantum field theory beyond the entanglement theory, even in 3 dimensions. And do we have a quantum material realize those topological quantum field theory? And so that's one of frontier research in condensed matter. Yeah.
Thank you very much. That clarifies and bridges nicely different aspects of our science. So we need that. Okay. Yeah. Thank you. Other questions?
If I may, I indulge myself, ask a short question. You mentioned...
Absolutely. Go ahead, Guan.
Near the end, you said Einstein's relativities and the equation will not be quite well described by these qubits. Yeah,
we are unable to do that. I think probably we can do it, but at the moment we don't know how.
So the question is, maybe Einstein's theory could not be really interpreted based on quantum qubits.
Exactly. I totally agree with you. And you can see in quantum qubits, we still work within quantum mechanics.
Exactly, yeah.
In quantum mechanics, time is absolute.
Exactly, and he did.
But Einstein's relativity even shake the foundation of time.
Yes.
And if time, so you can see, I'm not talking about space is dynamical. I did not talk about time is dynamical. When time is dynamical, then I don't know what I'm talking about. I think we have to really generalize quantum theory, and that is maybe that's a next revolution, Yeah. And so maybe just for the reason we couldn't get the Einstein equation, maybe for the good reason, because we work within quantum theory with absolute time.
Yeah.
That seems does not sound right. Yeah, and.
Yeah, that's what I was thinking.
Yeah. But other things okay. That's actually originally, before this, I thought some other property probably also require go beyond the quantum mechanics. So I'm pretty surprised the quantum mechanics can go so far. Those fundamental properties very weird. It's hard to imagine they can come up.
Yeah, that's reason Einstein.
Yeah, except quantum Einstein equation, yes, other probably can come up with qubits. Yeah,
we can follow up.
Yeah,
thank you, Xiao.
Yeah.
Okay, if there are no further questions, thank you very much indeed, Xiao, for a wonderful talk. Thank you.
Yeah, thank you very much. It's my pleasure, really. I enjoy it. Thank you.